Hi, this is Mrs. Verbal. This is part 3 of covalent bonding. So in the first two videos, we talked about what is a covalent bond, how do we identify it. We also looked at polar covalent bonds and how you can determine whether or not something is polar. And we also looked at the different types of bonds and how to identify the various types. Now we're going to start looking at the geometry of a molecule, and we're going to use the valence shell electron pair repulsion idea to help us determine what is the structure of the molecule. So the first compound that we want to look at is ethene. Ethene is actually naturally found with ripening of fruit. So if you have bananas in your kitchen and you put them in a brown paper bag, eventually the gas would accumulate, and that would help to turn the bananas from green to yellow. Now notice with ethene, we're looking at multiple bonds. So we have a total of 5 sigma bonds. So there's one between the two carbon atoms, and then there's 4 sigma bonds between carbon and hydrogen. Notice that there's one sigma bond and its location is above or below the carbon-carbon bond. Okay, here's another molecule. This is ETHENE, which is actually acetylene. And if you haven't seen my demonstration using acetylene, please let me know and I will show it to you in class. Here we have 3 sigma bonds, but we also have 2 pi bonds. So we have a pi bond here, and then we have a pi bond here. So it's essentially a triple bond between carbon, and then one single sigma bond on either side. And actually, just to let you know, miners would use acetylene gas to light the lamps that are above their heads. Okay, here we go. Now there's something which we call resonance. If you do the water goblet trick where you have a crystal glass and you fill it a certain height of water and you run your finger around the edges, you can actually get some resonance with sound. Well, there's something a little bit different with chemical resonance. You can have 2 or more dot diagrams, and the interesting thing is that neither one is considered incorrect. But what happens is electrons can move around with covalent bonding, and that's essentially what happens with resonance. And I'll show you a picture of this here. So we have NO3-. This is actually a polyatomic ion, and notice it has a -1 charge, okay? So what happens is the way the electrons are, they float or they travel between the 3 oxygen atoms. So notice we have a double bond here, and then it shifts over here, and then eventually it comes down here. Each structure is correct. It's just that there's no preferential treatment between the different oxygens. If you were to stop and freeze these structures in one time, you know, a third of them will have a double bond here, a third of them will have a double bond here, and a third of them will have a double bond there. Okay. Yeah. I mean, this is just a way to let us know that sometimes we take not artistic license, but we're just showing that the electrons are going to partially reside between each oxygen. And this double bond just shows you that because of resonance, we're going to have multiple bonds, and they're going to be shared equally between the 3 oxygens. Okay, here we go. I am not going to have you do all of these, but I'll just highlight the ones that we're going to do together, and then I'll tell you which ones you want to do separately. Okay, so the first one I'm going to show you is HNO3. The second one I'm going to show you is CO2. And then the third one I'm going to do is CH2O. Now the ones you're going to do on your own are NO2. You're going to do C3H4 and then N2O. Okay, now the question is, how do I do a dot diagram? Well, let me show you. There's a specific way of doing it. So the first one here, I have HNO3. The best way to do it is to write down the chemical formula first. So HNO3. Now what I want to do is I want to calculate how many outer electrons are there for each atom, okay? And the way I do that is I have to go to the periodic table. Okay, so here's my periodic table. Oops, I just lost it. All right, let me just bring it up again. Okay, so here's the periodic table. And what I want to do is I want to look at HNO3. So hydrogen we know has one outer electron. Nitrogen, the way you figure out the number of electrons is you just count across from left to right. So 1, 2, 3, 4, 5. And notice that oxygen has a 6th electron. Okay, so let's go back to our drawing here. Okay, so I'm going to start off by writing my chemical formula, which is HNO3. Now, I said that there's one outer electron for hydrogen, there's 5 for nitrogen, and then there's 6 for oxygen, but I have a subscript of 3. So I want to multiply that by 3, and I get 18. When I add all these up, I end up with 24. Now, you might ask yourself, where do I start? Well, I typically pick the least electronegative atom to put in the middle, and nitrogen has lower electronegativity than oxygen. Temptation would be to use hydrogen, but hydrogen can only take 2 electrons, so there's no way it's going to be in the middle. So I'm going to put nitrogen in the middle, and then I'm going to put the 3 oxygen around, and I'm actually going to put hydrogen next to one of the oxygen, because I know from previous experience it's not going to work going on top of nitrogen. All right, I'm going to draw 3 lines, and that represents the bonds around nitrogen. So I have 2, 4, 6 electrons. So I'm going to take 24 minus 6, and that gives me 18. I'm also going to draw a line between hydrogen and oxygen, and that'll essentially be 18 minus 2, which gives me 16. Now the goal is to have 8 electrons around each atom, and I'm going to, before I do anything with nitrogen, I'm going to add 2 lone pair electrons to oxygen. And let me see, I'm going to add 6 here. So I have 2, 4, 6, 8, 10 electrons. I'm going to subtract that, and right now I have 6 left. Now let's see if these atoms all have enough electrons. Hydrogen only needs 2, and it's good. Oxygen here, it has 2, 4, 6, 8, so it's good. This oxygen here has 2, 4, 6, 8, so it's good. Nitrogen only has 6, and this oxygen just has 2. Now this is where we have to figure out. We only have 6 electrons left. So if we did 2, 4, 6, we would have enough around oxygen but not nitrogen. So I'm going to actually draw another bond here, and then I'm going to add 2 more. So 2, 4, 6. Okay, we use up all of our electrons. Now let's make sure that nitrogen and oxygen have enough electrons. So 2, 4, 6, 8. This one has enough electrons, and then nitrogen has 2, 4, 6, 8. So it's good. All right, so I'm going to go back. I said I want to do CO2. So we're going to go to the next example here. Okay, so if you remember from the periodic table, Carbon has 4 valence electrons, and oxygen has 6, but we have a subscript of 2, so we want to put 12 there. So we end up with 16. So, question is, which one is in the center? Well, carbon has the least amount of electronegativity, so I'm going to put oxygen on one side, oxygen on the other. And then I'm going to draw a line between the two of them. So 16 minus 4 gives us 12. Okay. Carbon needs 2 more sets of electrons. Each oxygen needs 2, 4, 6 more. So we're in trouble here. If we put 6 on each oxygen, we don't have enough for carbon. So I'm actually going to double up here. Okay, so that's 4 electrons. So 12 minus 4 is 8. And then I have 2 oxygens. I'm going to divide that 8 into 2. Okay, so I used up all my electrons. Now the question is, does each atom have enough electrons? So let's see, this oxygen is 2, 4, 6, 8. It's good. This oxygen is 2, 4, 6, 8. This is good. And then carbon has 2, 4, 6, 8. So that's good. Okay, I want to do one more with you. I'm going to do NO2. Okay. Okay, so the last one I'm going to do is NO2, and actually I'm going to do NO2 minus, so just to let you know, it's different than what you see here. So when you're looking at, sorry, trying to get my pen back. We're looking at a ion. So NO2 minus. So nitrogen has 5 electrons. Oxygen has 6 times 2, which is 12. And if I have a negative charge here like I do, I actually have an extra one. So when I add these all up, I get 18. Now for nitrogen, it's the least electronegative, so I'm going to make it the middle atom. And then I'm just going to draw 2 lines there. And I'm going to take 18 minus 4, leaves me 14. Now I have to be careful. I have to make sure that all of the atoms around nitrogen have 8 electrons. So we would need 2, 4, 6. 6 times 2 is 12. We could do that and we'll be left with 2 left. But the problem is if we just put 2 electrons here, we only have 6 for nitrogen. So we need to make a double bond in order for nitrogen to be happy. So one of these oxygen is going to have has a double bond. So 14 minus 2 gives us 12. Okay, now this oxygen just needs 2 more electrons to be satisfied. So 2, 4, 6, 8. So we're going to subtract 4. And we're left with 8. Now, this oxygen only needs 6 electrons to be satisfied. So if we have 6, we are left with 2. So in this situation, I'm just going to put 2 on top because they're left over. And we've now used all our electrons. So let's double check and make sure everything has an octet. So here we have 2, 4, 6, 8. This oxygen is happy. This oxygen we have 2, 4, 6, 8. It's happy. And then for nitrogen we have 2, 4, 6, 8. So it's happy. Okay, and I'm just going to put brackets around here to show that this is a negatively charged ion. It's just a convention that we tend to do with dot diagrams. Okay, so you're going to do C3H4, and I'll just let you know there's going to be 3 carbons in a row, and one of them is going to have a multiple bond. N2O, and then I believe that's it. All right, be ready for the video assessment.